Good afternoon, everyone. I'm Annie from HKUST, the Hong Kong University of Science and Technology. It's my great honor to be here to present in the EC3 conference. Today, I'm going to share my recent research about a two-stage MEP installation constructability optimization system integrating DSM-based module division and 4D simulation. To begin, let me talk about the background. Traditional piece-by-piece MEP installation is inefficient and risk due to the high complex layout of the MEP design, as the figure shows. To solve this, the industry is shifting to modular MEP or multi-trade integrated MEP. So by prefabricating module design for offsite and bringing them to on-site installation, we can achieve higher quality, shorter control period, and less accident. Or in other words, we have higher constructability of modular MEP. However, implementing MEP introduces new challenges. The challenges are mainly twofold. The first, the complex interdependence makes it difficult to cluster the MEP elements into modules because module division need to consider on-site constraints, which is very complex. Second, the installation environment is highly dynamic. Like the video shows, newly installed elements will become the obstacle immediately, which the traditional method ignores this dynamic. So addressing these problems, our solution is to use dependent structure matrix, DSM, for module division, and 4D simulation for installation optimization. Here's the overall framework, which has 3 stages. Stage 1 is dynamic environmental modeling. We extract different information from IFC and then construct a 4D simulation environment within the ROS, robotic operating system. And in stage 2, the MEP module division, we evaluate the dependence of different elements and then cluster the elements with high dependence using the DSM. And in stage 3, in stage 3, we optimize the module installation. We will evaluate the path or of the installation. We can calculate the cost of each pass, and we can also diagnose the path. If we found some high cost installation, we can find out the high cost installation, the in-operate module division that causes the high risk, high cost installation. And then revise feedback this information back to the module division. So it's a closed loop optimization. Oh, sorry. Okay, let's dive into the first stage to build a robust simulation. We need to extract the constructability related information from IFC data. We pass the entity like flow sediment, IFC flow fitting, etc. And we aim to get 3 types of information: geometrical information about the dimension, about the shape, about the placement; production information about the weight, about the material, about the assemble type; and the function information about the role of the elements. And then within those extract data, we established a 4D simulation environment within rows. Here, the structural elements are served as static environmental constraints, and the corridors, doors are served as a traversable space. And by combining those 2 spaces, we can get a continuous collision-free configuration space. Within this configuration space, we can guarantee our simulation results is comply to the real-world application. Moving to the second stage, MEP module division, we quantify how different elements are related by this DSM heat map. The total dependence are the sum of 2 dependence, the topological dependence, mainly about spatial and and the connection and the functional dependence about the operational and the system capability. So by calculating it, we can get the dependence. And based on the DSM, we use a hierarchical clustering algorithm that iteratively merge highly dependent MP elements while considering the on-site constraints. Here we consider 4 types of constraints: dimensional constraint for transportation, payload constraint for equipment, gravity stability for preventing tipping, and the clustering coefficient preventing the unsuitable structural type. And then go to the third stage, module installation optimization. Once we get the initial module division, we need to find out the best installation sequence and best installation paths with lowest installation cost. Here we consider our cost from 3 perspectives: manipulation cost for movements, personality cost for penalize the getting too much close to the obstacles. This is dangerous for installation, and the smoothness cost does avoid the zigzag shape or some strange trajectory. And to accurately calculate the path, we use the artificial potential field or APF method. This method, you can imagine that there was an attractive pull force from the obstacle from the target position, while the obstacle generate a repulsive push force. The module's trajectory is guided by the less force of those 2 forces. So we can, by this method, we can ensure a collision-free path. And however, initial module division can cause some trajectory anomalies, such as some violent oscillations. So rendering module unsuitable for install. To resolve this, our feedback mechanism identify module violating the kinematic or spatial criterion. We analyze the root cause, such as the oversized branch, and feedback this information back to the module division part, and then the system will take some adaptive correction action such to redivide the module and to solve this trajectory issue. And to validate our method, we apply it to a complex underground parking garage. It features with dense multi-discipline networks across confined zone. So it's a perfect test case for our method. Here's the result of the module division. On top left, we show the module division results of 100 selected elements. Different color represent a different module, and on the top left and the top center, it shows the dependence value of different elements and the DSM heat map. And on the bottom, we show the path for different divided module with a green line. So it validates the robustness of our method in different scenarios. And then we analyze the optimization results. So the feedback loop, several high-risk elements causing the zigzag anomalies were identified, like the figure shows. We identify a very high-risk module, a very high-risk element, and redivide this module and solve the anomalies. And quantitatively, we compare the installation cost of different methods. Our method has very significant improvement than without module division, and also higher than normal module redivision feedback. This proves the significant improvement of the constructability of our method. Finally, let's summarize our research. We have 3 contributions. First, the IFC-based 4D simulation, and then the DSM-based module division. Finally, feedback-driven optimization, and within this feedback mechanism, we can refine the inoperator module division using the trajectory information, and this enhancing the overall constructability of the installation plan. Okay, then thank you. Go to my This is my end of my presentation. Thank you very much for your time and attention. I will be happy to any question.